Hello Chem 1B, this is chapter 16 lecture video 5 and we're going to be talking about weak acid solutions. So as you probably learned in Chem 1A, weak acids only partially dissociate, meaning they do not ionize 100%. What this means is that when trying to calculate pH of a solution that contains a weak acid, we can't assume that the concentration of weak acid is equal to the H3O plus concentration like we do in strong acid solutions. This is because the weak acid doesn't 100% form H3O plus. We actually get what a mixture of ions, so H3O plus and the anion of our acid, and unionized acid present in the solution. Because of this, weak acids, when put in water or any other solution, reach equilibrium. So HA here is just my generic weak acid formula. It's going to react with water, form H3O plus and A minus. H3O plus, of course, is the same thing as H plus. And that's kind of like the acid concentration that's actually present. Now, this is a significant difference from strong acids, right? Strong acids don't go to equilibrium, weak acids do. And kind of like Kw, we have a special K value for weak acids. Instead of calling it KEQ, we call it Ka, A being for acid. And as a generic weak acid thing, it's going to be the H3O plus concentration in the product side, the conjugate base A minus in the product, so in the numerator, and finally our unionized acid concentration, HA, as a reactant, so in the denominator. It behaves just like any other equilibrium constant, so it just gets a special name because we have a lot of different weak acids and they're all kind of labeled with a Ka value to be more specific. The larger your Ka, the stronger the acid. Now, it's important that you notice this ER here. I'm not saying the larger Ka is, it suddenly becomes a strong acid. That's not true. If you have a Ka, it's a weak acid because strong acids don't have equilibrium constants since they don't go to equilibrium. But the larger your Ka value gets, the stronger your acid is because that means you're more product favored, which means more of the acid ionized. So that's the answer, right? The acid dissociates more when we have a larger Ka value, which means we form more ions, more H3O plus in solution. So when we're doing problems with weak acids, they're pretty much just the same types of calculations we saw in the last chapter. We have ice tables. The new thing is with these problems versus last chapter's problems is pH is involved generally. And pH can either give you the equilibrium concentration, or you could be trying to solve for pH depending on how the problem is worded or the context of the problem. So let's do an example, right? The pH of a 0.1 molar solution of formic acid is found to be 2.38 at 25 degrees Celsius. And we want to know, hey, what's the Ka for this acid? Or what's the percent of the acid that actually dissociated, right? Percent ionization or dissociation. Well, first we need to write out our chemical equation. We know this acid here is going to react with water to form its conjugate base, HCH or CHO2 minus 1. H3O plus is another product. It's reacting with the water. Here's our acid. Right now, after this, we can write out an ice table. Equilibrium problems, we use ice tables. So let's do that on the next slide. So we have our ice table. We also have our equilibrium constant expression, since that's what we're trying to solve for first. We were told that we initially have 0.1 molar formic acid present in the solution. We also know we really don't care about the water because it's a pure liquid. Now, initially, I can say that both my H3O plus and my formate CHO2 minus is 0 molar initially, right? Because we weren't told anything about them, and just like we learned in the last chapter, if you're not told anything about the initial, it's 0. So next, we can fill in the rest of this ice table, right, with X and all that. But actually, we do know our equilibrium, wrong one, concentration of H3O plus as well, because I know the pH, right? So if I know pH, I can say, hey, well, we know that pH and H3O plus concentration are related to each other, right? Specifically, the H3O plus concentration in a solution is equal to 10 to the negative pH. So if I plug that in, which is what I did here, all right, 10 to the negative 2.3, I get my equilibrium concentration of H3O plus, which means I can fill that value into my ice table. Well, this tells me that now I know my change for H3O plus, because it went from 0 to 4.2 times 10 to the negative 3. So the change had to have been plus 4.2 times 10 to the negative 3. And since this whole reaction is 1 to 1 to 1, we can fill in the other change for formate, CHO2 minus 1. It would have to be equal to H3O plus, and for formic acid, it has to be negative 4.2 times 10 to the negative 3. This allows me, as we did in the last chapter, to add these two rows together and get my equilibrium concentrations for everything, right? And after this, now I can just kind of plug into this equilibrium constant expression, right? 4.2 times 10 to the negative 3 squared all over 0.96. Or sorry, 0.96. And this will give me my Ka value. So plugging that in, we get this guy like I just showed, and that gives us 1.8 times 10 to the negative 4. So what's the percent dissociation, right? Well, we know that HA initially was 0.10 molar. And we want to know, hey, what percent of this guy dissociated? Well, I know I subtracted 4.2 times 10 to the negative 3 from it to get 0.096 molar. Well, this, absolute value of this value is how much dissociated. And so my percent dissociation, we'll just say dis, is equal to 4.2 times 10 to the negative 3 all over 0.10 molar. And then, to get it in percentage format, times 100. So if we do all that, and this is pretty much always going to be the case for percent dissociation, it's your initial divided by your change. Or sorry, your change divided by your initial times 100. So, right, we know change divided by our initial. We have our change here, that's 4.2 times 10 to the negative 3. Our initial was 0.01, or 0.10 molar, which gives me a percent dissociation of 4.2%. As you can see, this weak acid dissociates very little in terms of acid strength and all that. It's pretty weak. We can also calculate pH for a weak acid if we know the Ka value. For instance, niacin, which is in vitamin B3 or is vitamin B3, has a Ka value of 1.6 times 10 to the negative 5. And we want to know, hey, what's the pH if I have 0.01 molar of niacin present in solution? Now, I don't know about you, but I have no idea what the formula of niacin is. I'd have to look it up. So, but instead of doing that, why bother? We know it's a weak acid, and so we can just write HA. And that's what I want you to do pretty much. If I give you a formula, you just don't know the if I give you an acid, you just don't know the formula of, just write HA, it's fine. Now, at this point, I can fill in what I know to my ice table. I know I have 0.01 molar of my weak acid initially, right here. And I know that I don't care about water because, again, pure liquid. I also know that initially I wasn't given any information about H3O plus or A minus, so they must be 0. Now at this point, we want pH, right? And we know pH is equal to the negative log of the H3O plus concentration. Well, that means I need this value here so that I can plug that in there and solve for my pH, which means I need to calculate the equilibrium concentration of H3O plus. So I need to plug in some values here. Let's say that's X. This means my change has to be, plus X. My change in A minus must have been plus X. My change in HA must have been minus X, and I can kind of fill in my last row here. This is done almost identically to what we covered in chapter 15. So next I can set this all equal to the Ka expression and the Ka value as given in the problem. And I get x squared is over 0.01 minus x is equal to 1.6 times 10 to the negative 5. Now, this is a relatively small equilibrium constant. When we're using the 5% rule, we generally want the equilibrium constant to be smaller. The smaller it is, the more likely it's okay to use. In this case, it's definitely. So I'm going to do it. I'm going to use the 5% rule and get rid of that minus x there, which simplifies my equilibrium expression. It's no longer a quadratic. This makes life so much easier. To simplify this a little bit more, I can multiply both sides by 0.01 molar. And this, will cancel this guy out. And then I'll get x squared is equal to 1.6 times 10 to the negative 7, which is relatively simple to solve, right? We just square root both sides. And we get x is equal to 4.0 times 10 to the negative 4. And if we remember back from our ice table, our H3O plus concentration was equal to x. So now that I know my equilibrium concentration of H3O plus, I just need to plug that into my pH equation, take the negative log of it, and I'll get my pH of the solution, which is 3.4. Now, you should always double check if this is actually less than 5% of 0.01. It is, so we're okay. But you should always double check that, because if it's not, then you can't use the 5% rule still, and you need to solve the quadratic. So let's do one more example problem, and then we'll finish this video off. What is the pH of a solution of 0.2 molar HNO2? The Ka of HNO2 is 4.6 times 10 to the negative 4. So first things first, I'm going to write out my equilibrium here. I have HNO2 reacting with water, and that goes to H3O plus, aqueous, and NO2 minus, also aqueous. Now I need to write out an ice table. Again, pure liquid, we don't care about water here. We know our initial concentration of HNO2 is 0.2 molar, and we weren't told anything about these two, so we're going to assume 0. Next, we write in the change. We know it's changing in this way, so it's minus x plus x plus x. We get 0.20 minus x, x and x. And then I can go, okay, well, Ka is equal to the H3O plus concentration times the NO2 minus concentration all over my HNO2 concentration, which, I know this value, and I know these values with respect to x. So 4.6 times 10 to the negative 4 is equal to x times x all over 0.20 minus x. And I'm going to assume the 5% rule, and we'll double check my work in a second, but we're going to assume 5% and just kind of get rid of that minus x there and solve this this equation for x at this point. So in order to do that, we're basically just multiplying both sides by 0.2 and then square rooting that value. So if you do all that, you get that x is equal to 0.00959 molar. Now, just to be sure, let's double check to make sure x is within 5% of our initial concentration. So I need to go, okay, 0.2 times 0.05, what is that, right? And I get that that's equal to 0.01. Now, is x less than 0.01? Hey, just barely, but it is, so we're good. Now we're asked for pH. We know pH is equal to the negative log of H through a plus, right? This value, which we have here now is because it's x, so 9.59 times 10 to the negative 3. We just take the negative log of that. And we get 2.02 as our answer. All right, so if you have any questions, as always, please reach out to me via email or my discussion sessions.